You've definitely learned exponent rules before, but I feel like we all forget them, even though it's kind of like the basis of algebra, right? So a lot of what we do when we are factoring or multiplying different factors out, or thinking about like if I add two lines together, what's going to happen? That all has to do with our exponent rules. And it all has to do with kind of like the building blocks of algebra. So if we don't really know this, then we're going to struggle later on with other things when we move to higher order functions. So the first thing I want to go over is when we have two of the same base with different exponents being multiplied together, right? So two expressions with the same base, different exponents being multiplied together. And I just want to review what happens. So when I say we have the same base, I'm saying like we have an x and an x equals x, like they're the same thing, right? I could have an m and an m, I could have a 2 and a 2, I could have a 5 and a 5, I could have a 100 and a 100. As long as those two numbers or letters are the same, then we are good to go. If they are not, then this rule will not work on them. So you'll notice, right, we have this m right here and the n, and when we multiply x to the m and x to the n together, we get x to the m plus n. And I know I just used a lot of letters, and I know that sounded very confusing. So if we look at an actual example over here, we have x to the third times x to the fourth, and we need to figure out what we get. And so this rule is telling us that if we have the same base and different exponents, they could be the same exponents, but as long as the bases are the same and we're multiplying them together, we just add the exponents. Right, so I end up with an x to the 3 plus 4, which is just x to the 7. So if we have x to the 3 times x to the 4, we really just end up with x to the 7th because we just add the exponents together. And I think a lot of the times we get confused with that when we're multiplying like x times x, right? Well, x has an imaginary 1 for the exponent, so x times x is always x squared. And I think a lot of the times we forget that and we just kind of drop the squared, but that's wrong. So if we look here at the next example, we have 2 to the 5th times 2 to the negative 1. And this one's a little different looking because 1, we have a negative exponent, and 2, we have the base of 2, not x, right? But the rule is still the same, nothing changes. So I have 2 to the 5th times 2 to the negative 1. And so I add the exponents together. So that turns into 2 to the 5th plus negative 1, which gives me 2 to the 4th. Right? I'm just going to highlight this in yellow, highlight this in pink. So we see that we're doing the same thing here because 5 plus negative 1, right? That's just saying I have 5 things and I take 1 away. So now I have 4. So I end up with 2 to the 4th. And that's all great and fine. And we're really happy about that for multiplication. But what about when we're dividing, right? So when we multiply, we always add exponents. And when we divide, we always subtract exponents. So for example, I just want to reiterate one more time that this again only works if we have the same base, right? So you can see here we have an x here and an x here. That's the only reason why it works, right? So if I have x to the 10th divided by x to the 4th, I end up with x to the 10 minus 4, which just gives me x to the 6th, right? So I'm just subtracting the exponents as long as the base is the same when we're dividing. So if we look here, I have 5 to the 4th over 5 to the 7th. And I end up with 5 to the 4 minus 7. Well, 5 to the 4 minus 7, if I have 4 things and I take 7 away, right, I go into the negatives. So I'm left with 5 to the negative 3, right? And we can think about that on a number line as well. If I'm at 4, I like to use 0 as like a placeholder, right? Like I know where 0 is in relation to everything else. And I go back 7. Well, I know that from 4 to 0, that's 4. And then to go 3 more would take me to negative 3. And then we have other exponent rules that are also very important, but you probably don't hear them as much as, multiply, add exponents, divide, subtract exponents. Let me just fix that so it actually looks like the word divide. But if we have a base raised to an exponent, and then that whole thing is raised to another exponent, we multiply the exponents together, right? So in this case, we have x to the 4th raised to the 3rd. We multiply 4 times 3 together, and we just end up with x to the 12th. So if we're going to do the same thing here, I have 10 to the 5th raised to the 6th. Well, that just gives me 10 to the 5 times 6. 5 times 6 is 30. And I end up with 10 to the 30th power. And then our next rule is really important. If we raise anything to a 0, we always get a 1. So anything raised to 0 equals 1, always, no matter what, right? So if I have y to the 3rd over y to the 3rd, right, I subtract those exponents, so I get y to the 0. Well, anything to the 0 power is just 1, so it just equals 1. So if I have 9 to the 0, it just equals 1. And then our next rule is kind of just like more of a notation rule. So if I have x raised to a negative exponent, that's just really saying 1 over x to the exponent. To make this happy, we have to move it down to the denominator. So in that example, we can say I have x to the negative 2. That's just the same way as saying 1 over x squared. Right? If I have 3 to the negative 1, that's just the same thing as saying 1 over 3 to the first power. So that's just really a notation rule that we can rewrite it. And that's really helpful when we're thinking about canceling things out from the top and the bottom and just really simplifying expressions. That's really helpful. And then the last thing we're going to look at is kind of this like funky square root. So we're used to a square root, right, as just being this little house. And when there's no number written, we assume it's a square root. So we assume that the number is 2. But what's really fun is that if we have kind of a fractional exponent, that's telling us that we're raising our base to something, but we're also taking the root of it. And the fraction tells us what we're raising it to and what type of root we're taking. So we can see here this fraction, x to the 4/5, is saying that we're raising our base to the 4th, and then we're taking the 5th root of it. And you can see here, we have 8 to the 2/3. So that's saying that we're raising 8 to the 2nd power, and then we're taking the cube root of it. And we can do this out because there's a more simplified answer. So 8 squared is 64, right? 8 times 8 is 64. And then this is saying, okay, we're taking the cube, right, root of 64. And the cube root is saying what number times itself 3 times gives me 64? And at some point, once you do this a bunch of times, you'll memorize, right? That, okay, well, 4 times 4 gives me 16. And if I do 16 times 4, I get 4 times 1, which is 4, plus 2, which is 6. So I get 64. So the cube root is 64, right? The number that has to be multiplied by itself 3 times to give me 64 is just 4. So 8 to the 2 over 3 really just equals 4. So I would say that the first four rules have to do with kind of getting a number out. This fifth rule is really more notation based. And then the last rule is really a combination of notation and getting an answer. Hopefully you remember these because when we move on, right, because this always comes back when we do like box method problems and stuff like that, we move on to a situation where we look like this. I want to make sure that we know for sure that 2x times 3x is 6x squared, right? I don't want to have to go through this again. So our job is to memorize these rules so then it makes the rest of algebra really, really easy.